Okay, in this video, let us continue with the discussion on differential amplifier for differential inputs. Okay, let us again consider. So we are considering a balanced differential input where we have this as VID by 2 and the input voltage on the other side is minus VID by 2. You can see we are applying two different input voltages of same magnitude. So that's why it is called as balanced differential input. So as we discussed in the previous video, so we're going to get V01 with respect to VIT. We name it as gain of the amplifier with differential, but it is single-ended. So ADS stands for it's gain of the amplifier differentially applied input voltage, but measured is single-ended. So that is V01 by VIT is given by minus GM into minus GM RD by 2. If we assume the value of RD to be 1 kilo ohm, and if we assume this as 1 milliampere and W by L is equal to 10, and of course if we assume the value of Kp as 200 microampere per volt square and VTO as equal to 0.4 volt, the gain of this amplifier comes out to be, I think, this divided by 2 and this divided by 2, because this is actually GM into RD, and then this happens to be 0.35. Okay, now I'm getting a gain of suppose, okay, as we discussed in the previous class, the GM is actually, suppose if I substitute the value of GM, this is the value of no, this is the value of GM is 1.41, so into 1000, because 1.41 exponential minus 3 into 1000 divided by 2. Okay, the gain is 0.7. Okay, it's not divided by 2, the gain is 0.7. Okay, this is the gain, and the gain is again here it is minus 0.7, here it is 0.7. The differential gain is, you can see now I have given a suffix of gain of the amplifier with differential input and differentially measured. So since it is plus here minus here, this is how it is measured with respect to VID. So this comes out to be GM into RD. You can see this is 1 volt. That's what we saw in our LT spice. So let us just have a look at the same thing. So this is my input voltage, and if I see this is my actually what I'm saying is this is VID by 2. VID by 2 peak to peak is 200 millivolt. So this is the peak and this is the other peak. The peak to peak is 200 millivolt for VID by 2. So naturally VID becomes 400 millivolt. I can see what is this voltage, which is now V01. If you see it here, it is out of phase with the input voltage VID. Let me also just make sure that this is a different color. Maybe this is fine. You can see these two are actually out of phase, and most importantly, so what you can observe here is, let me just go back to my, so we are measuring V01 at this point. So naturally this is the swing that is available from minus 0.9 to plus 0.9. This is the 0 point. Of course the applied input voltage is pure AC signal. The applied input voltages keep varying here. You can see this is varying around 0. It is varying around 0 because this doesn't have any DC voltage. So but the output voltage that is measured at this point, which is V01, will have some DC shift. So if you actually find out what is the DC voltage at this point, it is exactly VDD minus ID into RD. So if you actually find out the point at which your output is swinging, this is your output, how it is swinging. So from here to here, since this is VDD, it is, this point is, suppose if I write it as VD1, which is the DC voltage at the drain of M1, so it is down by ID1 into RD. So ID1, we know that it is ID1 is 500 microampere, RD is equal to 1K. So naturally, if this is 0.9 volt, so then this is actually 0.5 volt. So how do you got this as 0.5 is, ID into RD is equal to 500 microampere multiplied by 1K. This K and micro will become milli, so this will become 500 milli. So from 900 millivolts, so you come down by 500 milli. So this naturally is at 0.4 volt. It's at 0.4 volt. If you can actually see here, what I'll do, I'll go to simulation. Maybe what I'll do, let me for the time being, let us make this as this amplitude also as 0, and let me make this also as 0 amplitude, and let us see what is the DC voltage. Let me save this and see. Can you see this voltage? The voltage V01 is exactly at 400 millivolt. So why it is at 400 millivolt is because, as we saw here, so the DC voltage at drain of this particular transistor is VDD, which is 0.9 minus the drop. Drop is actually 500 millivolt. Because why it is 500 is because out of tail current of 1 milliampere, it is equally divided among both the transistors. And then since why it is equally divided is because we have the dimensions of the transistor same. So 500 milliampere, sorry, 500 microampere going here, and the 500 is going here. So the drop happens to be 500 millivolt. So 900 minus 500 millivolt corresponds to 0.4 volts. So that's why we have this is at 0.4 volt. Suppose if I apply a voltage over here, maybe something like, okay, 100 millivolt. You can see now I will apply 100 milli, and I will apply 100 milli here also. Let me apply 100 millivolt. I'm applying 100 millivolt and run it. You can see over this 400 millivolt I'll get the waveform. See now, this is exactly oscillating around 400 millivolt, meaning this is oscillating around 400 millivolt. Same thing will happen for this. So because here also the same amount of current is flowing, this is also at 0.4 because 0.9 minus 0.9 minus 0.5 happens to be 0.4. This is also, suppose if I see the voltage at this point, that will also come at the same point, but it will be in a opposite polarity. You can see here it is exactly at the same DC level. So let me just change this color to, okay, let it be red. Let me change this color to something different. Okay, let me make this. Okay, these two are the things what I have. Just a minute. If you can actually see both the voltages at VD1 and VD2, their DC voltage are 0.4 itself. So you can see this is for VD1. For VD2 it will be exactly in the opposite direction. That's what we are seeing here. This is exactly going in the opposite direction. This is going in the opposite direction, of course, which will be actually in phase with your input signal, which is in phase with your input signal. You can just go back here and then see this is actually the magenta one is actually in phase with the green one. But again, the magnitude of the gain is GM into RD by 2, which is 0.7, and this is also 0.7. Only thing is that they are out of phase. And most importantly, when you actually see the differential voltage, that is what we have here is the input voltage that is coming from VID by 2. Suppose if I say this is VID by 2, and this is VID minus VID by 2. Suppose if I say minus VID by 2 is just exactly the reverse one. The reverse one, you can see it is around 0. If you see what is V01, if you want to write V01, it is around VD1. It will be exactly in opposite to this phase. So you can see this is exactly in opposite to this phase. So these two are actually opposite. And coming to V02, this is again at VD2, I can see VD2 is actually in phase with this VID. You can see it is actually in phase with this VID. So this is oscillating around VD2, this is oscillating around VD1. So in this case it is shifted by 0.4, this is also 0.4. Fine. Suppose if I see now, this is V02. If you see V02 minus V01, that is differential output voltage, you can clearly see that the differential voltage will be a pure AC signal whose average is 0 volt. You can see it will be around 0 you're going to have, and it is always in phase with this. You can see they are in phase. This is going, this is also going. So this is the differential output voltage. Of course the gain of this happens to be Gm into Rd. This is Gm into Rd by 2. This is also Gm into Rd by 2. Here it is out of phase with the input, in phase with the input. See here, this is shifted by it is oscillating at around VD2. This is oscillating at around VD1. Because we know that VD1 is equal to VD2 is equal to VDD minus ID into RD. Assuming that okay, both the currents are same and both the resistors are same. So it was happening to be okay, in this case 0.9 minus 0.4, which was no, this was 0.5, so this was coming out to be 0.4 volt. So at 0.4 it was swinging. But interestingly, if you see the differential output voltage, it is oscillating around 0. So let me just go back and see here. So what I'll do, I'll go back to this and I'll measure V02 minus V01. V02 minus V01. Interestingly, you can see this blue one, which is V02 minus V01, is around 0. So this is whatever differential output voltage you'll get from a differential amplifier will be a pure AC signal, whereas the single-ended output voltages will be shifted by some DC voltage. That some DC voltage is VDD minus ID into RD. VDD minus ID into RD. So that's what I want to say here. So this is the input voltage. This is the input voltage. These are the two single-ended output voltages. If you want to write the output voltage of the differential one will be exactly over here. It will be like this. You can see this is around 0. This is around 0. Of course, the amount of amplification depends on what is. You can see this is how it looks. So this is your V02 minus V01. This is V in, and this may be V02, and this is V01. So this way we can able to see they are in phase, out of phase, and of course not only in phase, out of phase, whether it is having a reference at 0, whether it is having some shifted by DC voltage, all those things can be very clearly observed over here. You can see these V01, V02 are the two single-ended output voltages, whereas the blue one, so let me make it different color. Let me make this. You can see this is actually a differential voltage, which is a pure AC signal. But of course, the input is also pure AC. Let us see what is the impact of putting a resistor across this what current source. Let me put a resistor R of whatever value. Usually the resistor value will be very high across the resistor. Let me connect that. I'm just trying to connect. Okay, let me hold this and bring it down. Okay, this is done. Let me make it around 100k. Let us try to see what are the operating conditions, dot OPs. So in dot OP, what we are trying to understand is what is the voltage at V01, V02, the DC voltages, which will be 0.4, and this was how much? Current flowing was 500 microampere. This is also 500 microampere. And of course, VGS was something like 1.107 volts. So all those things we can able to verify. With this resistance, let us first do without resistance. Let me just cut this and try to do dot OP here. Where is this? Okay, I'll do dot OP, and then I will simply run it. See, now these are the voltages. So you can see V01 is 0.4, V02 is also 0.4, and then you can see because you cannot see VGS here. Let me just see VGS over here. Can you see VGS is 1.11, which is perfect here. You can see this. Okay, okay, VDS is almost 1 point. Okay, VDS is not required, so I'm interested in what is this VD, which is 0.4 here, which is V01, V02. The DC voltages at V01, V02 is 0.4. Let me put the resistor. Let me put the resistor and try to see what is. Okay, I will put a resistor. Let me make this DC again. I put a resistor of 100k here. Let me save it and then run. See, there is no. Okay, what is V01? Hardly there is no much change. It is almost at 0.4. It's almost at 0.4. V02 is almost at 0.4. See the current. Current is almost 500 microampere. Can you see it is 498 microampere, which is very close to 500 microampere. Meaning, we assumed in the discussion when the this particular potential there is, since whatever current you have here, so whatever current that is going here, the entire current goes back. So we consider this as virtual ground. Even though if you put a resistor of whatever value, since there is no current flowing here, this voltage still looks like zero. So that's why it is called as virtual ground. So even if I put a typical resistance of 100 kilo ohm, there will be no change in the analysis of your uh, amplifier, considering the input as a differential input. This is only true if the input is differential. If the input is differential, no current flows here. That's why this looks like a virtual ground. So there is no impact of this for a differential gain. Gain still remains whether you put a resistance of 100k or whatever. Suppose even if I put a resistance of 100k, 10k or 200k, these equations are still valid, because there is no question of, suppose if I say this as RSS, this RSS will never come out here, because this is open circuit, the same current flows here. Since there is nothing flowing here, this still looks like a 0 volt, which is the virtually it looks like 0 volt. So that's why there is no impact of RSS. That's what we saw in case of by seeing the dot OP. Let us do dot tran and try to see is any change in the gain of the amplifier or not. So gain of the amplifier has to be 0.7 single ended and 1.4 the differential. Okay, this is done. Let me change this to transient. This is fine. Let me save and then run it here. Let me see the input voltage. Let me just measure the input voltage peak to peaks. So this is let me write it. What I'm looking at now is this is with RSS is equal to 100k. We found that VD1 is equal to VD2 is equal to 400 millivolt, 400 millivolt, and we are trying to see what is VID, what is V01. Let us measure peak to peak. This is again peak to peak, and this is V02 peak to peak, then V02 minus V01 peak to peak. Let us measure these voltages. Actually what we are measuring is VID peak to peak by 2. So this is what we are having. Let me just since V in 1 is VID by 2, let me measure the peak to peak of it. Since it is 100, this is minus 100, I can simply write it as 200 millivolt. See here, I can write VID by 2 peak to peak is 200 millivolt. So from this I can write VID as equal to 400 millivolt. This is peak to peak. Then what is V01 peak to peak? This is V01. Let me just measure the peak to peak voltage of this. This is the peak to peak. If you can see, it is 276. Or if I just zoom it and then try to measure it properly, you can see this is almost 278, 279 or 280. 280 millivolt, and of course same thing in the case of V02 also. Let me measure that also. This is V02. Let me measure peak to peak of this. This is one peak, this is the other peak. It's again 280 millivolt. Let me measure V02 minus V01 peak to peak, that is this and this. You can see it will be a pure AC signal. You can see this is around 0. Let me just measure it across. Okay, this is, can you see now it is almost 560 millivolt. So since we are looking at AD of S, which is nothing but V01 by VID or V02 by VID peak to peak. And what is A? Okay, I'm just looking at these values. ADD, that is differential gain with differential measurement. V02 minus V01 peak to peak by VID peak to peak. So this comes out to be okay 280 millivolt by 200. Sorry, it's actually the reverse. Okay, what is V01 peak to peak? Okay, it's not 200, it's 400. So it is 280 by 400. It is 280 by 400. You have it as 0.7. This is 0.7. The expected gain is also 0.7. So here it is 560 divided by 400. It is 560 divided by 400. It is 1.4. So even when you put a resistor of 100k, the gain expressions and the measurement values will never change. So it is 0.7, 0.7, and then it is 1.4 volt. That is two single-ended gains and the differential gain. So there is no impact of the resistance across a current source for analyzing the differential gain when the input, or single-ended gain and the differential gain when the inputs are differential. So we have applied a balanced differential input and we are trying to verify what is the impact of this RSS on the expression or the gains. We found that hardly there is no impact of this RSS for a differential input voltage even when you measure the voltages as single-ended or differential. In the next video we will see what is the analysis of your differential amplifier if I apply a common input voltage. Now instead of applying two different input voltages at V in1 and V in2, let us apply common voltage and try to see what is the impact of that on the entire response.